So let me begin by giving a summary of the last lecture. Let me redraw the circuit. So I have a resistance R, I have an inductance L, I have a capacitance C, all three of them connected to a source of alternating voltage given by Vt equal to Vm sin omega t. So we had seen that what the role resistance played in DC circuits is defined to be impedance, which depends on the values of R, L and C and is usually denoted by Z, which is given by R square plus Xc minus XL whole square. And we had seen that Xc is given by 1 over omega C and XL is given by omega L. So this is capacitive reactance and this is inductive reactance. Now notice, unlike resistance, the impedance of course depends upon the values of R, L and C, but it also depends upon the frequency of the source. And we had seen that corresponding to this source voltage, the value of the current I is given by Im sin of omega t plus phi, where the amplitude of the current is given by Vm over Z and phi is the phase by which current leads the voltage. Now, what we did last time is also to look at a graphical interpretation of what's happening. Suppose I take the direction of the current as this. Now remember that the direction of the current is the same as the direction of the voltage drop across the resistance. So I will write this direction as VR, which is actually equal to I times R, which is also along the direction of current. Now, if you recall that an inductor, the current lags the voltage. Another way of saying that is, for an inductor, voltage leads the current by 90 degree. So therefore, if in the same diagram, I am drawing the voltage across the inductor, I'll draw it like this. So this is, let's say VL. And for a capacitor, since capacitive voltage would lag the current because capacitive current leads the voltage, I would put the capacitive voltage along this direction and let me, without loss of any generality, take the capacitive voltage to be larger than the inductive voltage, and of course if the reverse is true, then my drawing would change accordingly. Now, so therefore the net voltage due to the inductor and the capacitor, because they are aligned oppositely, would be obtained if I subtract from Vc VL. So this would come, let's say here. So this is minus Vc minus VL. Now what I do is this: if I complete this parallelogram, then this would give me the direction of the source voltage. So let's call this Vs for the source. And of course, this rectangle would be in the upper half plane if my VL were greater than Vc. Now, this angle phi is the angle by which the supply voltage lags the current. The angle by which and here, since the voltage lags the current, the circuit is dominantly capacitive. So let me give a few more examples over what I did last time. So I have a 100 microfarad capacitor in series with a 40 ohm resistance, which are connected to a 110 volt, this is RMS, 60 hertz supply. The question is, what is the time lag between the current maximum and the voltage maximum? Okay, first, since it's a 60 hertz supply, which is a linear frequency, so 60 hertz corresponds to omega equal to 2 pi times 60, which is approximately equal to 377 radian per second. So this capacitive reactance is one over omega c, and that's equal to 1 over 377, and c we have given is 100 microfarad, so that is 10 to minus 4 farad, and that if you calculate works out to about 26.5 ohms. I can immediately calculate the impedance of the circuit. Impedance of the circuit is obviously 40 square plus 26.5 whole square, and that if you calculate works out to approximately 48 ohms. Now I've given you the voltage in RMS, so I can immediately calculate how much is IRMS, the current. So the RMS current is simply 110 divided by 48, which is equal to 2.29 amperes, and this corresponds to a maximum or the peak current, which is obtained by multiplying this 2.29 with square root of 2, and that's equal to 3.24 amperes. Now notice that in this case, since I have only a capacitor and a resistance, that's it's an RC circuit, my current leads the voltage. Now the angle by which current leads the voltage, is given by phi equal to tan inverse of xc over r, and that if you put in the numbers and look up a trigonometric table, it works out to 0.58 radians. Now the time lag between the voltage maximum and the current maximum is obviously given by phi by omega, and the reason is the expression for the current is Im sine omega t plus phi, whereas the corresponding expression for the voltage is Vm sine omega t. We know that sine omega t becomes maximum at t is equal to pi by 2 omega, whereas sine of omega t plus phi becomes maximum when t is equal to pi by 2 omega minus phi by omega. So therefore, the lag between current maximum and the voltage maximum is given by phi over omega. The time lag between current and voltage maxima is phi over omega, and that's equal to 1.55 milliseconds. Now let's see what happens if I increase this frequency. So if I take the linear frequency f to be equal to 1 kilohertz, which corresponds to a value of omega which is given by multiplying this number with 2 pi, and that's equal to 6283 radian per second, and omega times c is 6283 multiplied by 100 microfarad, that is 10 to the power minus 4 farads, and that's equal to approximately 0.63 omega inverse, and correspondingly 1 over omega c, which is equal to your xc, this works out to just 1.59 ohms. I can calculate the impedance Z because the resistance is 40, so 40 square plus 1.59 square root, and that works out to about 40.03 ohms. Now look at what is my xc by r. Remember, my xc is small now, 1.59. So this 1.59 divided by 40 is equal to 0.039, and correspondingly the tan inverse of this, since this number is rather small, the phase phi is tan inverse of xc by r, which also works out to approximately 0.03 radians. And this time lag that you get now is given by 0.039, that is phi, divided by 6283, and that's equal to 6.3 into 10 to minus 6 seconds. So you notice the current is gradually becoming almost in phase with the voltage. In other words, as I increase the frequency of supply, the capacitor is becoming more and more conductive. Remember, for a DC, the capacitor was an open circuit and did not allow the current to pass. So with increasing frequency, the capacitors turn out to be more conductive. So last time we did the graphical analysis of the LCR circuit. So let me now take the mathematical analysis, and that goes as follows. I can write down it is the analytical solution. So using Kirchhoff's law, the loop law, I can write down the equation as L di by dt plus IR plus Q over C is equal to Vm sin omega t, where Q by C comes because that is the voltage drop across the capacitor. Now this equation can be converted into a second order differential equation either in charge or in current. So observing that I is equal to dq by dt, you can do that. I decide, since I am only interested in current for the moment, let me differentiate this equation once more. So we get L d square I over dt square plus R di by dt plus 1 over C times dq by dt, which is equal to I, that's equal to Vm omega cosine of omega t. So look at this equation. The right hand side is a trigonometric function, and on the left hand side I have got current I and its differentiations once or twice with respect to time. So what I do is I assume a solution of this form. I is equal to Im sine of omega t plus phi, where phi, as I have explained several times, is the phase by which the current leads the voltage. And if you differentiate it once, you get di by dt equal to Im omega cosine of omega t plus phi, and a second differentiation gives me d square I over dt square equal to minus Im omega square sine of omega t plus phi, minus because the differentiation of cosine gives me minus sign. And if you substitute these things into this equation that we have, I get Im omega, I get minus L omega plus 1 over omega c times sine of omega t plus phi, then plus r cosine of omega t plus phi, that's equal to Vm omega cosine of omega t. And of course we need to determine what are these quantities Im and phi. So what I get from here is Im omega minus L omega plus 1 over omega c times sine of omega t plus phi plus r cos omega t plus phi, and that's equal to Vm omega cosine of omega t. Observe that this quantity here is xc minus xl. I can simplify the left hand side of this expression by taking r equal to some a cosine theta and xc minus xl to be equal to a sine theta, where of course I need to determine what are a and theta, but you can immediately see from these two relationships, I have a square equal to a square cos square theta plus a square sine square theta, which is r square plus xc minus xl whole square. And that, if you recognize, is nothing but the impedance square z square, which tells me that a is simply equal to z. and tangent of theta is obtained by dividing the second by the first, is xc minus xl divided by r. Now, with this identification and cancelling the common terms omega from both sides of this equation, I get Im z cosine of omega t plus phi minus theta. That is just because I have taken this r to be a cos theta. So, this is a cos theta cos omega t plus phi, this plus a sin theta omega t plus phi. So, this is what I get, and that quantity is equal to Vm cosine of omega. Now, if you compare the two sides of this expression, what I get is Im times z is equal to Vm, which tells me that the maximum current or the current amplitude is given by Vm divided by z, and this theta is simply equal to phi. So, my solution is given by I equal to Im, which is Vm over z sine of omega t plus phi with tangent of phi, which is now have been shown to be equal to tangent of theta, equal to xc minus xl divided by r. Now, let us look at an interesting property of LCR circuit, and this is known as the resonance. The phenomena of resonance you have come across even in mechanical circuits, for example, a driven pendulum. Now, we know that when the driving frequency equals the natural frequency of the problem, then the amplitude rises substantially. Now, this phenomena is called the resonance. So, let me look at what are the properties of this resonance now. So, I maximum is Vm divided by square root of r square plus xc minus xl whole square, where xc is 1 over omega c and xl is omega times l. Now, notice one thing, that the impedance is minimum. Impedance is what is there in the denominator. So, impedance is minimum, implying thereby that the current is maximum when xc becomes equal to xl. So, when 1 over omega c is equal to omega l, that implies that when omega is equal to omega 0 equal to square root of 1 over LC. This omega 0 is my definition of a resonant frequency. Notice that the resonant frequency does not depend upon dissipative element like resistance. It is entirely decided by what the values of L and C are. And at the resonance, my current becomes maximum and its value becomes Vm divided by R. And the phase, remember we said that the tan phi is xc minus xl divided by R. Phase phi becomes equal to 0. Phase phi becoming equal to 0 means that the current is in phase with the supply. So, let us look at what it implies. Let me plot the current against the impressed frequency. Now, I will do it for different values of R. Now what you find is this, that as you increase the frequency, then your IM at follows a curve like this. So this, for instance, is for a particular value of R. So let's call it R1. Now suppose I now decrease the value of R, making it, let's say, R2, then what will happen is that it will become sharper and the maximum current will be more. And this frequency at which, so this was R1, this is R2, which is less than R1. So this is the frequency is omega 0, and this is of course my current. Now remember what is actually happening. In order to have a resonant frequency, I need both L and C must be there. And this is because, if you recall, the two reactances are aligned oppositely, and so therefore there is a cancellation which is possible between the XL and XC. The cancellation becomes exact at the resonant frequency and the maximum current rises. Now this incidentally is the principle by which various tuners work. For example, when you tune in a particular radio station, now what you find is, if you are going on rotating the dial, when your capacitor frequency of the circuit that is inside the radio tuner matches the natural frequency in which the signal was coming in, now that is the time when you receive the signal sharply. So this is what is used in radio tuning and many other tunings. Now having defined what is resonance, let me try to look at the sharpness of resonance. But before that, let's look at that. Suppose I am plotting the impedance Z. What type of situation they have? Now remember, at the resonant frequency, the impedance is minimum. On either side of the frequency, the impedance rises. Whether it is the capacitor reactance is more or the inductive reactance is more, that is totally immaterial, but look at what we are having. So what we get is something like this. Supposing this corresponds to, I am plotting it against omega, supposing this corresponds to omega 0, omega or frequency, doesn't matter. And so what happens is, in the capacitive section, I get this, and for inductive part, so this is XL greater than XC, this is XC greater than XL. Now notice, if omega is greater than omega 0, alternatively if omega square is greater than omega 0 square, then what we are saying is omega square is greater than 1 over LC. So that I have L omega greater than 1 over omega C, and L omega, if you recall, is the inductive reactance. So this is what we are talking about in this part, and reverse is of course true if I have omega square less than omega 0 square. Now what's the idea of this resonance? Now since the impedance is minimum, and you remember the current is proportional to 1 over Z, because current is basically, maximum current is Vm by Z. Then the current is maximum and the power which goes as I square Z. If Z is minimum, current is maximum, and I square Z, which is the power absorbed by the circuit, is also maximum at omega equal to omega 0. Now, there is a prescription for deciding how to measure the sharpness of these resonances. So, what we do is this, that when we increase or decrease the frequency from omega 0, starting with omega 0, I can increase the frequency or decrease the frequency. Then I look at that point where the power absorbed is half the maximum power absorbed. So let's look at that picture again. So this is my current, and this was the resonance. This is the way the Im varies with omega. Let me call it Im because I'm still talking about maximum current, and this is the value of Im, and this is actually the maximum as a function of omega. Now, so what we do is this, so this is where my current is maximum. So let me say this is equal to omega 0, and this value, let me just write it as Im maximum. So this maximum is as a function of omega. Now what we do is this, we increase the frequency starting from omega 0 or decrease the frequency on either side, and where we have the power, average power absorbed is half the maximum value. Okay, so increase or decrease frequencies, starting with omega 0 till power absorbed, average of course, is half the maximum power absorbed. This is what happens at omega 0. Now, remember that my power expression was at this point, because Z essentially is R, so I had I square R, that was the power. Now I want this power to be 50%, so 0.5 times that. So these are called half power point. Which I can rewrite as I by square root of 2 whole square times R. So basically I am looking at the points where the maximum current has dropped to about 70% of the value, that's 1 over square root of 2. So these are the 2 points. If you like, we'll call this omega 1 is the upper half power point and omega 2 as the lower half power point. This width here, so omega 1 minus omega 2, or alternatively, if you are looking in the language of the frequency, then correspondingly dividing it by 2 pi, that's called the bandwidth. So let's write this as delta omega. So this is bandwidth expressed in radian frequency. So you could also write it as f1 minus f2, which will be in hertz. So this is bandwidth. Usually bandwidth is just written as BW. So this is delta. Actually it is 2 times delta omega, because if this is delta omega, so this is also another delta omega. So this is my definition of the bandwidth. So let me now do a little more quantitative calculation. So let us suppose omega 1 is equal to omega 0 plus delta omega. We had said this is a higher half power point, and omega 2 equal to omega 0 minus delta omega. So I said that 2 times delta omega is my definition of bandwidth. So what it means is this: if you have a sharper resonance, then your bandwidth becomes smaller, because then the peak is much sharper. So sharper resonance implies lower bandwidth. Now let's look at the point omega 1. So at omega 1, I have got, so omega equal to omega 1, I have got Im equal to Vm divided by square root of r square plus omega 1 L minus 1 over omega 1 C whole square. And this is, by our definition of the half power point, is Im max divided by square root of 2. So which is equal to, since Im max is nothing but Vm by R, so it is Vm R into square root of 2 in the denominator. So basically what I have is this: by squaring both and doing some algebra, I get the following. I get R square plus omega 1 L minus 1 over omega 1 C whole square is equal to 2R square. And so that tells me that omega 1 L minus 1 over omega 1 C is equal to R. Now of course, if the solution of this equation is plus or minus R, it would depend upon which one to take, depending upon whether the inductive reactance is greater or the capacitive reactance is greater. But I already know that omega 1 is omega 0 plus delta omega. So this times L minus 1 over omega 0 plus delta omega times C is equal to R. So let us look at this. So let me take omega 0 L common. I am left with 1 plus delta omega by omega 0 minus, let's again take omega 0 C common here. I have got 1 plus delta omega by omega 0 in the denominator, and if I take it to the numerator using a binomial, I get 1 minus delta omega by omega 0, assuming delta omega is small, and that's equal to R. Now notice that by definition, omega 0 L is equal to 1 over omega 0 C, because omega 0 is the resonant frequency. So therefore, when you open up this, that term will cancel out, and I will be left with L times delta omega from this term, plus because there is a minus here, 1 over omega 0 C times delta omega by omega 0 that's equal to R, and this term is nothing but omega 0 L at the resonance frequency. So therefore, both these terms are L times delta omega. So I'm left with omega 0 L times 2 delta omega is equal to R, which tells me that delta omega is equal to R divided by 2L. I'm sorry, there is no omega 0 here because omega 0 cancels with this omega 0. We define the sharpness of the circuit through a quantity called the quality factor. So quality factor of a circuit is omega 0 by 2 delta omega, which is equal to omega 0 L divided by R, and that is represented by Q. So let me give you a few examples. I have a series LCR circuit which has a resonance frequency at, let's say, 1 kilohertz. So in a series LCR circuit, resonance frequency omega 0, actually I am giving f0 is equal to 1 kilohertz, and quality factor is given to be 100. Now suppose I double R, L and C are doubled, each of them is doubled. What would happen to Q? Now look at this. I know omega 0 is 1 over square root of LC. So if you double both L and C, then the denominator here will become increased by a factor of 2, so that omega 0 reduces by a factor of 2 if L and C are doubled. But remember, my Q is omega 0 L divided by R. So we have seen that omega 0 would reduce by a factor of 2, but since you are increasing both L and R, nothing would happen to this factor. So therefore, Q will become 50. Let me give you another example. Let me take an LCR circuit with the alternating voltage being given by 240 volts times sine omega t. I have been given L is equal to 10 millihenry, C is equal to 1 microfarad, and R is equal to 40 ohms. So let us find various data connected with the this problem. First is, let's look at what is resonance frequencies. Resonance frequency of the circuit is given by omega 0 equal to 1 over square root of LC. So L is given to be 10 millihenry, so that it is 10 to the square root of 10 to the power minus 2 Henry. C is 1 microfarad, meaning thereby 10 to the power minus 6. So taking square root, it is 10 to the power 4 radians per second. What is the amplitude of the current at resonance? So at resonance, the Im itself is maximum, that is the amplitude is maximum, and so Im max is given by Vm divided by R, that's equal to 240 divided by R, that's equal to 6 amperes. And the quality factor is given by omega 0 L divided by R. Here R was of course 40 ohms, and so that's equal to 10 to the power 4 there. L is 10 to the power minus 2 divided by 40, so that's equal to 2.5. What is the voltage across the inductor at resonance? So VL max, so that's obviously equal to Im max times omega 0 L, that's your reactance, which is 6 multiplied by omega 0 is 10 to the power 4 and L is 10 to the power minus 2 Henry, so that's equal to 600 volts. Let me give another example. Let's consider a circuit for which the inductance, I'll take it a rather large inductance, 3 Henry. Capacitance is 27 microfarad and resistance R is 7.4 ohms. What should be done if you want to improve the sharpness of resonance? By reducing the full width at half maximum, FWHM, by a factor of 2. So the question is, what should we do to reduce FWHM by a factor of 2? Well, remember that omega 0 is 1 over square root of LC, which is 1 over, now L is 3 Henry, C is 27 into 10 to minus 6. So this is 1 over 9 in the denominator and 10 to the power 3 in the numerator. So it is 111 radian per second. And the quality factor is omega 0 L over R, which is 111 multiplied by 3 divided by 7.4, and that's approximately equal to 45. Now suppose keeping omega 0 fixed, I want to reduce delta omega. So if I recall that the expression for Q is omega 0 L by R, one of the possibilities would be to reduce R, because I want to double Q, which is the same as doubling, reducing the width of the full width at half maximum by a factor of 2. So one possibility is of course to reduce R, which is resistance, or of course equally to increase L. But technically it turns out that manipulating inductance is a lot more difficult thing. In fact, what is done in LCR circuits is to use capacitors and resistances to be adjusted. That is because resistances can be varied by using variable resistances, and also it is possible to change capacitances. But manipulating L is lot more difficult, and hence the best that you can do is to reduce R by a factor of 2. So the solution would be to reduce R by a factor of 2. So let me quickly summarize what we did today. Earlier we had seen how to describe LCR circuit by graphical methods. So today we actually solved a second order differential equation and solved the circuit for current and obtained the analytical solution, getting expressions for both the current maximum and the phase lag that the current has with respect to the supply voltage. Having done that, we defined a property of LCR circuit known as resonance. And what happens is that if you are able to control the frequency of the impressed voltage, then at a particular frequency which is given by 1 over square root of LC, the current amplitude rises substantially, and that frequency is known as the resonant frequency. The property of the resonant frequency is that that is the frequency at which the circuit absorbs maximum power from the source. We defined the sharpness of resonance by finding out what are the half power points on both sides, that is, what should be the current value, current amplitude values, for which the power absorbed by the circuit is half the maximum power it could absorb at omega. And these two symmetrically located points where the current maximum is, the power maximum is halved, is what is known as full width at half maximum. And smaller this width is, sharper is the resonance. And with that in mind, we defined what is known as the quality factor of a resonant circuit.